Right, so this is chapter 2. We're going to look at first just modeling heat flow. Okay, so in this, what we're going to do is start with a very typical idea in physics. We're going to think of, say, an insulated rod like that. So we can either put heat in here or take heat out here, depending on what the temperature is, and we can do the same thing here at this end. But we're going to say that there's no heat exchange along the side. So all you have to do is insulate that, so you put a bunch of styrofoam around it or something like that. If you think of it that way, that's not going to let any heat out. All the heat has to travel through the ends. And so, they describe, something you could do. Well, I could put this into some, a refrigerator or something like that for a long period of time, so that we began with both ends and the middle, for that matter, being at 10 degrees, say, centigrade. So it could be any temperature. And this would be our T0, temperature 0. Okay. Now, once that's reached a nice steady state at 10 degrees through the whole thing, I guess you'd have sensors, or, you just have done this enough, you know how long to keep it there, whatever. Now, move it and add basically heaters. I think you could also think of them as coolers. That's just negative heat as cooling. Add heaters to each end. And observe how the temperature at each point along the rod changes over time. Okay, and so in this case, they give a very specific thing. They say, okay, well, there's the rod, and we'll put T1, we'll keep this end at 0 degrees centigrade. So that's actually cooler than it was. And T2, we'll keep this end at 50 degrees Celsius. Sorry, Celsius, not centigrade. Shows my age. And so, we're going to do that, and you do that just by having good equipment that can, keep those temperatures constant. And then, we can look at this at various times. So, for instance, if this is X, and this is U, the temperature, so U is the temperature, then what we would expect is, something like, here's 10, and, here's time 0, T0, something like that. Now, I'll use a different color here, and let's try red. I let this go for a little bit, and I check it again. And, what you might expect to see is if this is 0 down here, right? You know, this thing has changed temperature, but probably not through the whole rod. But the ends have gotten warmer. And we'll put 50 up here and 0 down here. And we might expect to see, you know, something like this at, this is T1. Then we'll get a different color here, maybe yellow. And give it a little more time. And, you know, you would expect that a little more of the inside of the rod has been heated up. And we get something like this, and that would be our T2. Now, if we let it go long enough, we'll reach a steady state. And at T infinity, or something way out there anyway, you would probably expect to see something like this. So this would be T infinity. And you would see that the temperatures at the left have all gotten cooler. The temperatures at the right have all gotten warmer. And at some point, they are 10 degrees somewhere in there because we're going between 0 and 50. And so, you know, that's the kind of thing we're expecting to see. So each of these is a U function, a temperature function, but at a different time. And that is why, you know, we say, oh, we've got U of X and T, okay, because it's going to be a different temperature at different locations at different times. And so we've got the function of both space and time. And now, so they just give us the model at this point. They don't derive it or anything. And they tell us that U sub t, and this is typical notation you'll see here. Now, you know, other notation would be the partial of U with respect to t. And this is the rate of change of U, the heat, with respect to, typically we write WRT with respect to time. And that is equal to, whoops, no equal to there, alpha squared U sub XX. So this is alpha squared. You could write the partial square root of U with respect to X, the space variable. So this is the concavity. Whoops, concavity of U with respect to X, or space. Okay, so this is interesting. Now, they shed a little light on this, and I'll mention it here, and then I'll actually start a new video where we go more into depth on this. But this says the temperature at any point, you know, or at some point, X along the rod. So we'll put that along the rod, is increasing. Okay, and then I'll put in parentheses decreasing for the other case. If the concavity the concavity of the temperature profile is positive. Okay, or negative for the decreasing case. Whoops, put that out there. Now, again, going back to this picture, we see that over here on the left, at this stuff where the red is on the left, that's concave down. And we see as we went through time, we had that temperature decrease on there, on that side. And on the right side, the curve started out concave up, and the temperature was increasing where we saw it being concave up. So that's the idea and the model. And we'll shed a little bit more light onto that model and some beginning insights into numerical methods to solve these things in the next video. So we'll stop this one here.